Welcome to the Rory Academy YouTube channel. We share valuable information about power electronics technology and its emerging applications. Today, we will be comparing the main features of an N-channel MOSFET with that of a P-channel MOSFET. But first, we will be reminding ourselves of the basic features of a power MOSFET. What is a power MOSFET device? A power MOSFET is a type of metal oxide silicon field effect transistor designed to operate at voltages up to 1 kV for silicon-based devices or more than 2 kV for silicon carbide devices while offering high switching speeds and optimal efficiency. This device is central to a wide range of applications. As illustrated above, a power MOSFET device is usually represented by a three-terminal symbol, namely gate, G, drain, D, and source, S. The most common application of a power MOSFET is using it as a switch in a power electronics converter. The construction of a MOSFET is like that of a field effect transistor, FET. An oxide layer is deposited on the substrate to which the gate terminal is connected, acting as an insulator. Hence, the MOSFET has another name as insulated gate field effect transistor, IGFET. The voltage at gate controls the operation of the MOSFET. In this case, both positive and negative voltages can be applied on the gate as it is insulated from the channel. With negative gate bias voltage, it acts as depletion MOSFET, while with positive gate bias voltage it acts as an enhancement MOSFET. The MOSFET is classified into two based on their modes of operation, i.e., enhancement mode and depletion mode. While an enhancement mode MOSFET can be further classified into P-channel and N-channel, and the same applies to the depletion mode MOSFET. In a power electronics application, the MOSFET works as a switch. It controls the voltage and current flow between the source and drain. When a drain source voltage, VDS, is connected between the drain and source, a positive voltage is applied to the drain, and the negative voltage is applied to the source. Here the PN junction at the drain is reverse biased and the PN junction at the source is forward biased. At this stage, there will not be any current flow between the drain and the source. When a positive voltage, VG, to the gate terminal, due to electrostatic attraction, the minority charge carriers, electrons, in the P substrate will start to accumulate on the gate contact, which forms a conductive bridge between the two N+ regions. The number of free electrons accumulated at the gate contact depends on the strength of positive voltage applied. The higher the applied voltage, greater the width of the N-channel formed due to electron accumulation. This eventually increases the conductivity, and the drain current will start to flow between the source and drain. When positive voltage is applied at VG as shown above, then the minority carriers, i.e. holes, get repelled and the majority carriers, i.e. electrons, get attracted towards the silicon oxide layer, insulating layer. With some amount of positive potential at VG, a certain amount of drain current ID flows through source to drain. When this positive potential is further increased, the current ID increases due to the flow of electrons from source, and these are pushed further due to the voltage applied at VG. Hence, the more positive the applied VG, the more the value of drain current ID will be. The current flow gets enhanced due to the increase in electron flow better than in depletion mode. Hence, this mode is termed as enhanced mode MOSFET. When no voltage is applied between the gate and the source, some current flows due to the voltage between the drain and the source as shown above. Let some negative voltage be applied at VG. Then the minority carriers, i.e. holes, get attracted and settle near the silicon oxide layer. but the majority of carriers, i.e. electrons, get repelled. With some negative potential at Vg, a certain amount of drain current ID flows from source to drain. When this negative potential is further increased, the electrons get depleted, and the current ID decreases. Hence, the more negative the applied Vg, the lesser the value of the drain current ID will be. The channel nearer to the drain gets more depleted than at the source, like in FET, and the current flow decreases due to this effect. Hence, it is called depletion mode MOSFET. However, in some applications, we require a P-channel enhancement mode MOSFET, where the load is connected directly to the ground. This is achieved because the P-channel MOSFET is upside down with its source terminal tied to the positive supply VDS. Then a positive voltage, Vg, to the source terminal, and the gate terminal is connected to the negative voltage. In a P-channel device, the conventional flow of drain current is in the negative direction, so a negative gate source voltage is applied to switch the transistor on. Remember to like, subscribe, and hit the notification bell. Thanks for your support.